Hello, all. Welcome to this course on computer organization. The topics we are discussing today are memory system, which includes the hierarchy, characteristics, and performance analysis, and semiconductor memories that include RAM, ROM, and EPROM. Let's begin. An ideal memory would be fast, large, and inexpensive. A very fast memory can be implemented if static RAM chips are used. But these chips are expensive because the basic cells have 6 transistors, which preclude packing a very large number of cells onto a single chip. Thus, for cost reasons, it is impractical to build a very large memory using the static RAM chips. The alternative is to use dynamic RAM, which have much simpler basic cells and thus are much less expensive. But such memories are significantly slower. Although dynamic memory units in the range of hundreds of megabytes can be implemented at a reasonable cost, the affordable size is still small compared to the demands of large programs with voluminous data. A solution is provided by using secondary storage, mainly magnetic disks, to implement large memory spaces. Very large disks are available at a reasonable price and they are used extensively in computer systems. However, they are much slower than the semiconductor memory units. A huge amount of cost effective storage can be provided by magnetic disks. A large yet affordable main memory can be built with dynamic RAM. This leaves static RAM to be used in smaller units where speed is of utmost importance, such as in the cache memory. All of these different types of memory are employed effectively in a computer. The entire computer memory hierarchy is as given in the figure. The fastest access is to data held in the processor registers. Therefore, if we consider the registers to be a part of the memory hierarchy, then the processor register are at the top in terms of the speed of access. Of course, registers provide only a minuscule portion of required data. At the next level of hierarchy is a relatively small amount of memory that can be implemented directly on the processor chip. This memory is called the processor cache. This memory copies instructions and data stored in a much larger memory that is provided externally. There are often two levels of cache. A primary cache is always located on the processor chip. This cache is small because it competes for space on the processor chip, which must implement many other functions. The primary cache is referred to as level 1 or L1 cache. A larger secondary cache is placed between the primary cache and the rest of the memory. It is referred to as L2 or level 2 cache. It is implemented using static RAM chips. Including a primary cache on the processor chip and using a large off-chip secondary cache is currently the most common way of designing computers. It is possible not to have a cache on the processor chip at all. Also, it is possible to have both L1 and L2 caches on the processor chip. The next level in the hierarchy is called main memory. This rather large memory is implemented using dynamic memory components, typically in the form of SIM, DIM, or RIM. SIM or single inline memory module is a memory module containing one or several RAM chips on a small circuit board with pins that connect to the computer motherboard. DIM or dual inline memory module comprise of a series of DRAM ICs. While contacts on SIM on both sides are redundant, DIM have separate electrical contacts on each side of the module. Standard SIMs have a 32-bit data path, whereas standard DIMs have a 64-bit data path. RAM stands for RAM Bus Inline Memory Module. It is a packaging for RDRAM or RAM Bus Dynamic RAM that is similar to DIM but use different pin settings. RDRAM was developed by Rambus for high bandwidth application as a replacement for various types of contemporary memory such as synchronous dynamic memory. That is synchronous dynamic RAM. The main memory is much larger but significantly slower than cache. In a typical computer, access time for main memory is about 10 times longer than the access time for L1 cache. Disk devices provide a huge amount of inexpensive storage. They are very slow compared to the semiconductor devices used to implement the main memory. During program execution, the speed of memory access is of utmost importance. The key to managing the operation of hierarchical memory system is to bring instructions and data that will be used in the near future as close to the processor as possible. Now let's look into semiconductor memories. They are available in a wide range of speeds. Their cycle times range from 100 nanosecond to less than 10 nanoseconds. When first introduced in the late 1960s, they were much more expensive than the magnetic core memories they replaced. Because of rapid advances in VLSI technology or very large scale integration, the cost of semiconductor memory has dropped drastically. As a result, they are now used almost exclusively in implementing memories. Now let's move into RAM. RAM stands for Random Access Memory. It allows data items to be read or written in almost the same amount of time, irrespective of physical location of data inside the memory. They are capable of retaining their state as long as the power is applied. The two main types of RAM are static RAM and dynamic RAM. Figure illustrates how a static RAM cell may be implemented. Two inverters are cross-connected to form a latch. The latch is connected to two bit lines B and B' by transistors T1 and T2. These transistors act as switches that can be opened or closed under the control of word line. When the word line is at the ground level, the transistors are turned off and the latch retains its state. For example, let us assume that the cell is at state 1 if the logic value at point x is 1 and at point y is 0. This state is maintained as long as the signal on the word line is at the ground level. Static RAMs are fast, but they come at a high cost because their cells require several transistors. Less expensive RAMs can be implemented if simpler cells are used. However, such cells do not retain their state indefinitely, hence they are called DRAMs or dynamic RAM. Information is stored in a dynamic memory cell in the form of charge on the capacitor, and this charge can be maintained only for tens of milliseconds. Since the cell is required to store the information for a much longer time, its contents must be periodically refreshed by restoring the capacitor charge to its full value. An example of a dynamic memory cell that consists of a capacitor C and a transistor T is given here. In order to store information in this cell, transistor T is turned on and an appropriate voltage is applied on the bit line. This causes a known amount of charge to be stored in the capacitor. There are many applications that need memory which retain the stored information if power is turned off. For example, in a typical computer, a hard disk drive is used to store a large amount of information, including the operating system software. Non-volatile memory is used extensively in embedded systems. Such systems typically don't use disk storage devices. Their programs are stored in non-volatile semiconductor memory devices. Different types of this memory have been developed. Generally, its contents can be read as if they were static RAM or dynamic RAM memory. But a special writing process is needed to place the information into this memory. Since its normal operation involves only reading of stored data, a memory of this type is called ROM. ROM stands for read only memory. Data stored here cannot be electronically modified after the manufacture of the memory device. They are useful for storing software that is rarely changed during the life of the system, also known as the firmware. Figure shows a possible configuration of a ROM cell. A logic value 0 is stored in the cell if the transistor is connected to the ground at point P, else a 1 is stored. The bit line is connected through a transistor to the power supply. To read the state of the cell, the word line is activated. Thus, the transistor switch is closed and the voltage on the bit line drops to near 0 if there is a connection between the transistor and the ground. If there is no connection to the ground, the bit line remains at high voltage, indicating a 1. A sense circuit at the end of the bit line generates the proper output value. Data are written into a ROM when it is manufactured. Some ROM designs allow data to be loaded by the user, thus providing a programmable ROM or PROM. Programming is achieved by inserting a fuse at point P. Before it is programmed, the memory contains all zeros. The user can insert ones at the required location by burning fuses at that locations using high current pulses. This process is irreversible. Another type of ROM chip allows stored data to be erased and new data to be loaded. Such an erasable, reprogrammable ROM is usually called EPROM. EPROM stands for Erasable Programmable Read-Only Memory. It ensures that memory changes and updates can be easily made. Its structure is similar to ROM. However, connection to ground is always made at point P, and a special transistor is used which has the ability to function as either a normal transistor or as a disabled transistor, that is, always turned off. This transistor can be programmed to behave as a permanently open switch by injecting charge into it that gets trapped inside. The important advantage is that their contents can be erased and reprogrammed. Erasure require dissipating charges that is trapped in the transistor of the memory cells, and this can be done by exposing the chip to UV light. For this reason, they are mounted in packages that have transparent windows. That's all for now. Thank you. Thank you for listening.